Good afternoon, everyone. Wherever you are in the world, I hope you and your loved ones are healthy and safe. My name is Randy Bell, and I'm the director of the Global Energy Center at the Atlantic Council. And for those of you who follow this series regularly, as promised, I have shaved my beard. Thank you for joining us again for EnergySource Innovation Stream, where we highlight new energy technologies with the potential to reshape the global energy system. Today, we'll be hearing from Dr. Jose Reyes, Chief Technology Officer and co-founder of NuScale Power, who's coming to us from Corvallis, Oregon, to discuss latest advances in small modular reactor design, commercialization, and deployment. Before we get started, two administrative details. First, you can follow us on Twitter at AC Global Energy and use the hashtag InnovationStream. Second, after Jose's presentation, you can submit questions through the Q&A function on Zoom, and I will try to get to as many of these as I can. If you're watching on another platform like YouTube, unfortunately, we cannot take your questions. So please let me welcome Dr. Jose Reyes to the Atlantic Council. Jose, thank you so much for joining us.
Well, thank you so much for inviting me. It's a real pleasure to be on the program.
Oh, we're so glad to have you here. So how is the new world of COVID-19 treating you, and how have you and NuScale changed your operations in response?
Well, it's been a pretty dramatic change, although we were able to go to remote working very quickly. I was actually pretty surprised at how straightforward that was. About 98% of the workforce is currently working remotely from homes, and it's been good. It's been very good. Progress continues to occur. We're still on our schedule, so we're excited about that part of it. But it's been a challenge, kind of being apart from other folks and being able to see them face to face and shake hands and things.
Yeah. I don't know if we'll ever be shaking hands again. We may be just elbow bump from now on.
That's right.
But good to hear that the progress is ongoing. We're very much looking forward to hearing about NuScale's SMR technology. And since you are the engineer and the genius behind all of this, we're really looking forward to hearing from you. So we're going to do this a little differently this time. The presentation is going to come from the Atlantic Council side. So Roger, if you can share your screen, and then Jose will get started with his presentation.
Okay. Great. Well, thanks again for inviting me to present. I'm very excited to be here. I'm a big fan of the Atlantic Council, keeping track of some of the work that goes on there. Some really valuable work in terms of energy. So let's go to the next slide. So I'll be talking about the future of energy, and in particular, I'll be sharing a little bit about nuclear power for the modern grid. So there's a lot of work that we've done that has come out of our interactions with numerous utilities. We meet with 29 utilities every 6 months, and they've been giving us feedback for many years at this point. And so part of what I'll describe is really what nuclear power looks like for the modern grid. So next slide. So we're committed to people, planet, and prosperity. We're a triple bottom line company. And our mission is to provide scalable, advanced nuclear power for the production of electricity, heat, and clean water. But the last part is the most important part, to improve the quality of life for people around the world. And so later on, I'll talk a little bit more about the fact that we're not just focusing on electricity, but also on clean water, hydrogen production, a whole range of applications, which really can expand the market for nuclear power. So next slide. So this is the long journey that I've been on, and our whole company's been on, moving up this mountain to take our design from the laboratory to the market, basically. It all started back in 2000 with a grant from the Department of Energy. So I was a professor at Oregon State University, and we did 3 years of work on that project. At the end of 3 years, we had a really nice design, We thought, wow, this is kind of groundbreaking stuff, and especially in terms of safety. So in 2004, I spent the year working with the International Atomic Energy Agency in Vienna. And what I learned there was that there was a huge market for smaller reactors, for small power. The need for something that would fit on smaller grids and was more economic. So when I came back to the US in 2005, decided to move this technology from the laboratory to the market. And we've been doing that ever since. So it's been quite a journey. We were very fortunate that early on I teamed up with Paul Lorenzini, who became the first CEO of NuScale. We formed the company together in 2005. Now John Hopkins is our CEO and is doing a fantastic job. Fluor came in as a lead investor in 2011, and that was huge for us. They helped us move forward very quickly. It was a really big plus to be working with Fluor. So that investment has continued to grow. So we have a public-private partnership, and about 2/3 of our funding comes from private sources. The remaining 1/3 has been coming from the Department of Energy. A lot of accomplishments along the way. Right now, we've submitted our design certification application to the NRC back in 2016. It was adopted in 2017. And we are almost there to the final safety evaluation report, which is scheduled to come out here September of this year. So we've made huge progress. We're about $900 million, actually $900 million plus in terms of investment in the project. We know that will be around $1.4 billion expended as we go to build the first plant. So our first delivery, we're looking at the first operation in 2027 in UAMPS, and I'll talk more about that. So next slide. So let me talk a little bit about the technology itself. So what you see on the screen is a NuScale Power module. It consists of a small reactor vessel, which is housed inside of a small containment vessel. So instead of the big concrete dome, what we've done is we've gone to a small steel containment. And during normal operation, that sits underwater. So the design is essentially a small reactor vessel inside of an evacuated steel shell underwater below ground. And that's the whole design. So it's each module produces about 60 megawatts electric. That's enough for about 50,000 homes. It would be enough to power Corvallis, for example. And our first project with the Utah Associated Municipal Power Systems is a 12 module plant to produce 720 megawatts. And that's will be sited at the Idaho National Laboratory. So the technology is fairly straightforward. It's a natural circulation system, so there's no reactor coolant pumps inside the reactor vessel. It's a high pressure containment, and it all sits underwater during normal operation. We'll go to the next slide. So here's the module. That's all made in the factory. So the reactor vessel, the containment vessel, all those components are actually fabricated in a factory. So if you go to next, each module then has its own location in a bay, which sits underwater. And so this shows the configuration for a 12 module plant. We're looking at other arrangements, so it's with less modules, of course. But that's each of these power modules or NuScale Power module is connected to its own dedicated turbine generator set with small skid-mounted 60 megawatt turbine generator set. Next. It goes into the reactor building. So that central building is reactor building. Everything you need for safety is right there in the reactor building. We'll go to the next slide. So it's a different model for the construction and operation of nuclear power. You have a factory manufactured module, which is shipped by truck, rail, or barge in 3-4 pieces, depending on the location of the site. Then it gets taken to the site where it's assembled. It's flanged back together. The fuel is shipped separately. And then each module produces its own power. So it's relatively independent. So you have 12 almost independent modules producing power up to 720 megawatts. The advantage of doing it this way is that while you're doing your civil construction on site, you can be doing your module manufacturing in parallel. And so that means you can cut your construction schedule from 5 years down to 3 years. So it's a huge savings in cost and schedule because of that one item. The other thing is that we can refuel the modules. We refuel once every 2 years, each module. And we can do it in a staggered manner. So that means I can refuel module 1 And while that's being refueled in a separate bay, the rest of the plant continues to produce power. So as a result, you're always producing power for this plant. And you have a very small refueling crew, which is a permanent crew that's part of the facility operations. So next slide. So simplicity, this is the simplest design you can imagine. Because of it, we've gone to a new level of safety. For this reactor, for any accident condition that you can imagine, no operator actions are required, no AC or DC power, and no need to add water for the reactor to keep it safe and cool for a prolonged, actually it's unlimited coping period. So it's very unique, and it's all done passively. So it doesn't require any AC or DC power or batteries. Next slide. Manufacturing, we spent quite a bit of time doing testing. About $100 million was expended testing our control rod drives, our steam generator at full scale, our control room. We've got a huge cadre of analysis and tools and manufacturing hardware that we've used and assessed over the years. Next slide. So this is when I talk about nuclear power for the modern grid. There really is a new level of plant resiliency. We provide a black start capability, island mode, meaning that any one module can power the remaining 11 modules. You can go to hot standby conditions if you're disconnected from the grid. And as a result, this design offers first responder power, which is new to nuclear power. It has a high degree of resilience, a significant seismic capability, greater than what you saw at Fukushima. It's a post 9/11 design, so it's resilient to aircraft impact. We're using field programmable gate array technology for cybersecurity. So it's a hard wired system as opposed to software. There's no operating system for our safety systems. And we've done some hardening for electromagnetic pulse. And we've published reports on each of those, and you can find them at our website. Next slide. Also, we've been looking at other applications. We've done oil refinery studies, hydrogen production studies, desalination. One module connected to reverse osmosis can produce 60 million gallons of clean water per day. A 12 module plant can produce all the water needs for a city the size of Cape Town, South Africa. We've also put in 3 different modes of load following so that we can work well with renewables. Next slide. Our first project, as I mentioned early on, is with the Utah Associated Power Systems. That's going to be in Idaho Falls, and we're looking forward to that. UAMPS is a great partner. It's their carbon-free power project. And so they have a great vision for what they want to see for their grid, a low-carbon grid providing power to their constituency. And so with that, I think we'll go to the next slide, and I think we can open up to some questions.
Great, that's fantastic. Roger, if you could stop sharing your screen. Jose, this is really remarkable, and we are getting a ton of questions already coming in, and so I want to try to make sure we get to as many as we can from the audience. But I wanted to take the prerogative of the moderator and ask you at least one first, which is you mentioned load following, which seems to be a game changer for nuclear in some ways. Now you hear about some good advances in France with load following to help balance renewables, but how can you go a little more into depth about how the NuScale technology can help follow load and help balance renewables and really move towards a zero carbon power system?
Right. Yeah. We've been working with potential customers for many years, since 2008. And we keep hearing several things. One is they've got quite a bit of renewables, wind and solar, variable power generation, and they needed something to balance the grid. So we've designed this plant for frequency hunting to stabilize the grid. We've also designed it so that we can do rapid load following, and that's a steam bypass, which is not the most efficient way to do it, but you can do that for minutes to hours. And then we do have a highly renewable control rod system that allows us to power for hour to days to follow solar, for example. It works quite well for that. And then over the long term, if you're working with hydro, we have what we call load shaping, which allows us to shut 1 or 2 modules down for a prolonged period of time. So there's lots of flexibility there. And this is a real interest right now because there's a growing energy imbalance market that we're seeing on the West Coast where we think this might fit in real well.
As I asked that question, two other questions popped up, just basically very similar to what I asked. So I think it's getting a lot of attention. So Joniel Cha from S&P was asking that, and then Michael Kirst asked if there was actual data on load following. So if that's something maybe we could share offline, how that works in more detail.
Yeah, we published the paper, and actually that paper is accessible. It's been peer reviewed, and it's accessible at our website.
Oh, that's fantastic. So Michael, your question is answered on the NuScale website. Michael had another question that I thought was pretty interesting. He asked about the harmonization of regulatory standards and if that can be done with Europe and Asia to help get at some of the cost savings that you're already sort of mentioning at the beginning. But is that one way of generating more cost savings?
Yeah, there's that would be a tremendous advancement, not just for our technology, but for all nuclear technologies. There's a lot of information, of course, that's being shared. As I mentioned, I worked for the International Atomic Energy Agency for a year, and that's kind of the body that would help do some of that with some international standards. But the challenge is, of course, is that each nation has its own regulations, has its own guidelines, and so to harmonize that has not happened yet. But there are folks who are interested in doing that, and it would certainly help in terms of having to relicense over and over again the same technology.
Mm-hmm. Yeah. I'm going to actually ask you another question about cost, because that's often the criticism of nuclear. It's perhaps unfounded, but nonetheless, there are large upfront costs for nuclear. How do you see NuScale's technology as ultimately cost savings across the whole value chain there, whether you're talking about making it in a factory or having it modular, et cetera?
Right. Yeah. By doing the modules and particularly the containment vessel in a factory, you really do save a significant amount. Instead of doing all that work in the field, you're doing it in a controlled environment. And we know that by the time we get to the 8th module, we will have probably reduced the cost of those modules, maybe up to 20%. We're looking at some of the experience that the Navy has had with submarines and building in factories, and we can expect something like that. But on top of that, the fact that this is a much simpler system, that we've eliminated so much in terms of external power requirements and things like that, because of the significant safety, we do see cost reduction there. So the cost, our target for the first plant is around 6.5 cents per kilowatt hour. So that's the target, and we need to be below that in order to work with UAMPS. And so that's competitive in their region with natural gas in terms of what they're looking for, plus the fact that they're using it as a carbon hedge. Many states now, of course, are imposing clean energy standards, and which will require eliminating some of the coal and natural gas that's out
there. Yeah. Fantastic. Okay, really good question from our friend Seth Gray, who thanks you for the presentation and asks how NuScale aligns with the goals of the Nuclear Fuel Working Group report that was released a couple weeks ago, and helping the U.S. nuclear power industry compete internationally.
I think that report was fantastic. I think it was very insightful, and not only that, it's quite actionable. It has steps that can be taken to strengthen the industry as a whole, and it could help lead us back to being leaders in nuclear power worldwide. So I think it's a really key report, and I hope that they'll continue to move forward with the steps that are outlined in that report. In terms of the fuel, I think there are some new fuels being developed, accident-tolerant fuels. There's a fuel being developed by Lightbridge, which is really a kind of a game changer. And I think those types of fuels would work well with our technology. And so I think there's opportunities there with the nuclear fuel improvements to move us forward, not just in the US, but worldwide.
Yeah, and my favorite part of that report is when at the very end it says, for additional reading, read these 5 other reports, and it cites a really, really fantastic Atlantic Council report on the value of nuclear power to the national security establishment. Yeah. So I really recommend reading that page where it recommends the Atlantic Council. We had another really good question about fuel from B. Jordan. I don't know the first name. Asks, what impact would the availability of HALEU, so a high-assay, low-enriched uranium, have on your plans when you were originally designing the system? Would you have thought differently about your design?
Yeah, we still look at the HALEU fuel as a possibility for later on if it was available. So certainly for our design, we're using the less than 5% enriched, so standard uranium oxide rod bundle fuel. But we look at some of the designs that are out there that would actually give us higher performance, as well as maintain the same or even an improved level of safety. And so we're excited about that. And some of those fuels are the higher assay fuels. So instead of a 2-year refueling, we can go to 3-year, 4-year, maybe even longer types of refueling outages, intervals. And that, of course, works into economics.
Mm-hmm. Fascinating. What is the nuclear has some of the highest capacity factor out there? Does NuScale's capacity factor, because you can actually do replace the fuel sort of sequentially, is it even higher?
Well, we would love to be able to do what the current industry is doing right now. I mean, it's phenomenal what's been done, and 98 to 99% capacity factors are the best in all the energy industry. So we'd be happy with that. So what we tell folks is that we're for the first plant, we're looking at beginning around 95%. We know we can do around 98%. And then if you have a good operations crew, certainly you can improve on that. But yeah, we would be happy to do what's being done by the current fleet. It's amazing.
Yeah, got it. Okay, an interesting question from Florence Low Lee. Would you please share or update on the progress made between NuScale and South Korea's Doosan Heavy Industries partnership?
Yeah, they're great partners. We're very excited that they've just recently was in the news that Doosan had invested in NuScale. They're great partners. They have great manufacturing capability, and so we're excited to work with them. And they actually have sent one of their engineers to work with us on a regular basis here in Corvallis. So that's been very positive. So we interact with them very well, and we're looking at the entire supply chain and where we might be building plants around the world. So it's a great partnership.
It's fantastic. Okay, a really interesting question from Diarmuid Foley coming in from Ireland. I hope I have your name pronounced right. If 6.5 cents per kilowatt hour is the target price for your 12-unit module, how does reducing the module number to say 6 or 8 units impact the dispatch price?
Right, that's a very good question. And so, you expect the price to go up. We're looking at that right now, and we're looking at 2-packs and 4-packs, and looking at ways in which we can reduce the levelized cost of electricity, basically.
Mm-hmm.
So, what we're finding though is that depending on where you're putting those modules, that you're competing not with natural gas, you're competing with diesel, basically. And so, I was recently in Puerto Rico, and they're paying 28 to 30 cents per kilowatt hour. And so when we say, hey, we can give you 8 cents or 10 cents, that's a game changer for them, because right now they're paying so much. And there are many parts in the world that don't need 700 megawatts. They only need 1 or 2 modules. I think it would compete well in those markets.
Yeah, that's really interesting. So a question came in on desal, which is something that we don't talk enough about. Wondering if you could explain the economics of desalinization with NuScale, and how it competes with natural gas.
Yeah, the big thing with desal is, we're using standard technology. We've looked at reverse osmosis and other types of distillation processes. And we found that with the RO filters, as good as they are now, they're fairly economic to do it that way. Now, whether your power comes from natural gas or your power comes from, electrical power comes from a nuclear plant, the only difference there is just that nuclear is carbon-free. And so the folks who are looking for a carbon-free solution to provide also water, it's a really good match. And of course, it's in modules, so you can go with 60 megawatts or 120 megawatts or whatever you need, and mix and match and provide power and clean water to a coastal city.
Mm-hmm. So staying on the topic of not electricity, one of the other possible uses of nuclear, and this is a question coming from Michael Yancey, one of the other possible uses of nuclear is producing heat for manufacturing, such as steel or aluminum. Can you use NuScale technologies for that? And if yes, are you in any conversations to do so?
Yeah, we have done some studies looking at other applications where you need higher temperatures. So our output temperature is around 300 degrees C, which for some processes might be too low. However, what we found, we did a hydrogen production study with Idaho National Lab using their high temperature steam electrolysis. We found that with a 6 a 6-module plant, you can produce about 200 metric tons of hydrogen per day. But what's interesting about that study is we only had to use 2% of our power generation to provide power to resistance heaters to take our steam from 300 degrees C to 850 degrees C for the flow rates that were being looked at for hydrogen production. And so you can still produce a significant amount of high temperature, high pressure steam, even with our lower pressure system. So that was a very insightful study. You don't need much peaking power to get the temperature you need for these different industrial processes.
Oh, that's fascinating. That's fascinating. Okay, a little bit less technical, but more to the ecosystem that we've created here in the United States. This is a question coming in from somebody named Greg. Greg, we don't have your last name here. But what was the role of the national labs in supporting your efforts to advance your reactors? Perhaps a little more broadly, what is their role in supporting advanced reactor technology?
Yeah, I think they have a very important role. Whenever you have a new technology, working with the national lab provides you the appropriate uh, background in terms of technical support, as well as the areas of the laboratory space to do some critical work. So early on, that was funded by the Department of Energy, and we worked closely with Idaho National Lab, and that was really foundational for us. And we continue to work, of course, now with Idaho National Lab as part of, in terms of the site, the first site for our UAMPS plant. But I think it's all part of de-risking new technologies. We work with, I mentioned, lots of different utilities, about 29 utilities. We meet every 6 months, and they tend to be risk averse, and they would like to be the second owner, not necessarily the first owner.
Yeah.
But what do you do to de-risk that first plant? So we know that the cost will continue to go down with this design with subsequent plants. But what do you do for that first customer? So by having the government come in, provide some cost sharing, provide some facilities, provide site opportunities, all those things are huge for de-risking the first of a kind. And I think it's true for all advanced reactors that it plays a pivotal role in moving that technology forward on an international basis.
Mhm. So we have a good follow-up question to this from an anonymous attendee. So I can't tell you who this question is coming from, but really asking more about the competition internationally. We have this great ecosystem that helps you get these technologies developed at home, but what considerations do U.S. firms need to compete with foreign companies when you're trying to sell your reactors abroad?
Yeah, that's a great question. You know, we're a small company. We're NuScale. We're about 500 employees and 6 offices in the U.S. and 1 in London. So we're growing. But when we go to other countries to sell, we're competing with foreign governments, and so the playing ground is not quite level. So it's this report that recently came out, the DOE report, I think is tries to address that, and I think if we follow those steps, it'll go a long ways, especially the fuel take back concepts that are being considered. Those steps will allow us to bring the best technology in the world throughout the world, and so we really believe that U.S. technology, the work that's being done on advanced reactors, that it's the best technology in the world, and if we had a level playing field, we would win. And so I'm looking forward to seeing what comes out of the studies from DOE and the actions that come out of that work.
Fantastic, thank you. And I'm sorry to all of those out there who have questions that we haven't gotten to. We are running out of time, unfortunately. We do keep these to a tight half hour in order to make sure that we use everyone's time appropriately. So thank you all for tuning in, and especially thank you, Jose, for your remarkable presentation.
Oh, thank you very much.
Oh, and we really love working with you guys. You can follow NuScale on Twitter at NuScale_power, and you can connect with Jose on LinkedIn. This presentation will be available on the Atlanta Council website, YouTube channel, Facebook, and Twitter. So please share it with your colleagues. And thank you to all of those who helped put this event together, including Olga Kokova, Gray Johnson, Natalie Merla, Roger Morales, and Lauren Holland. I hope you all will join us for the next edition of the EnergySource Innovation Stream next Wednesday, May 27th at noon Eastern Time, where we will speak with John Justus Schmidt, co-founder of Enactor, who will discuss AEM electrolyzers, which are highly efficient hydrogen generators. And then finally, if you're interested in transatlantic developments in energy, as we know NuScale is, the Atlantic Council Global Energy Center is thrilled to launch our latest report, European Energy Security and the Critical Role of Transatlantic Energy Cooperation, next Thursday, May 28th, from 8 a.m. to 9:15 a.m. Eastern Time. We have a really great lineup for that event, including Digital Jorgensen, Frank Fannin, and Ted Garish. So I hope you'll tune in. More information about this event is on the Atlantic Council website. So until next week, everyone, please stay safe and healthy out there. And Jose, thank you one final time. This was
Thank
really
you very much.